As we continue to do our vector treatment of rotational quantities, I now want to go and define angular momentum. I'm going to have to start at what's probably going to look like a little bit weird of a place, but hold with me and we'll work out, I promise. So, in order to do this in general, it turns out that you just plain can have to be able to define the angular momentum of anything, even if it doesn't seem like it's particularly spinning. So for instance, let's just say I have a mass that's moving in a straight line, constant speed here, or at least at this moment the velocity is this. And so the momentum will also point in the same direction, so I'll just kind of put that over there. Even though we can imagine that this might just end up going in a straight line forever, in a sort of a weird sense, it is still kinda sorta rotating about this axis right here. So that's actually where we have to start with defining angular momentum. So we'll go ahead and draw a position vector from our axis that we're choosing to analyze everything around. So this is our axis of rotation, and just this mass here is doing a really bad job of rotating around that axis, but it is still kind of sort of rotating about it. And then we go ahead and define the angular momentum of this point mass about that axis of rotation there as L. Yeah, I know, you're probably expecting a Greek letter, weren't you? Is defined to be R cross P. So in this particular example here, to take the cross product, I usually recommend redrawing these vectors so they're sitting tail to tail. R like that, and our linear momentum is pointing like that. And if we want, this is our angle phi, so we can get the magnitude by saying that it's RP sine phi. And so go ahead and just pause the video for a moment and see if you can figure out which way the angular momentum points here. All right, so remember to make the widget with your right hand. Put your first finger along R, then flip your hand around to get your second finger to match P. And what you should have gotten was that the angular momentum, in this example, points into the screen. Okay, that's a little abstract, but that is the angular momentum for a point mass. Now, if I have a system that's made up of more than one point mass, what you can do is you can just add them up. Now, for the actual sorts of spinning objects that we generally think of, you can eventually show. So I'm just going to assert here, you can show, but the analysis is beyond the scope of what we can do here, although I do have videos of it on the channel. You can show that L equals R cross P will eventually yield that the angular momentum of an object is equal to the moment of inertia about its rotation axis times the angular velocity. So say if I had a disk that was spinning like so, the angular velocity would point like that. Check that using the hitchhiker rule. Remember to make sure to use your right hand. And the angular momentum would point the same way. Now, an important caveat here is that this is only going to work, so this is only true for the long and short symmetry axes. of the object. So you may have remembered me mentioning earlier when I was making caveats about tumbling and stuff like that. In the case of, say, a tissue box, you can spin it around the long axis and it's stable, and you can spin it about short axis and it's stable. But if you spin it about the one that's intermediate between the two, you'll see that it tumbles. In that particular case, the reason why it's tumbling is because the angular momentum does not point in the same direction as the angular velocity. So in general, what you would have to do, and the treatment is beyond the scope of what we're doing here, is you would have to treat the angular momentum using by modeling it with an mathematical object called a rank 2 tensor, which for our purposes is a 3x3 matrix in this case. But that's beyond the scope of what we're doing, but I just wanted to put that caveat in there that there is still a little bit more under the hood. However, in a lot of practical application, the angular momentum is going to point, in a lot of practical application, you're going to be spinning an object about its long or short symmetry axis, or you may have situations like, say, a basketball or something like that. With a ball, any axis that goes through its center is the same long axis, or short axis for that matter, because they're all the same. So you can spin a ball about any axis you like. The angular momentum and the angular velocity will point the same. For a frisbee, you could have also chosen, say, to spin it about this axis here, and you could do that anywhere along the rim of the frisbee as long as it goes through the middle. Those would all be long axes, and the usual way you throw a frisbee is the short axis. So it turns out that any sane way that you would throw a frisbee is going to give you, we'll let you go ahead and apply this, where the angular velocity and the angular momentum point the same way. Or similar for a football or anything like that. So this isn't as restrictive as it sounds, and for a lot of practical application, this is all you need. So just to get a little more practice on this, let's go ahead and just find the angular momentum of an airplane that's flying overhead of you. So here's me, and here's a airplane, like so. There we go. Let's say the mass of the airplane is 10,000 kilograms, and it's going at 100 meters per second. We'll also say that I worked out that it was 5,000 meters away from me. Actually, let me just draw the line right to my feet there. It was 5,000 meters away from me, and the angle that we're making right here is 37 degrees. So let's go ahead and find the angular momentum. So first off, draw the vectors. First off, define your axis. Since I'm asking for the angular momentum about me, let's go and put the axis about me. So then my position vector will go from me to the plane like that. And then the momentum vector is going to point the same way as the velocity vector. All right. So again, I always recommend when you are thinking about the cross products, redraw your vectors once you have them so that they're tail to tail. That makes it easier to think about it. R, P, like that. So now go ahead and use the right-hand rule to figure out the direction that the angular momentum points. Okay, so in this case here, once again, the angular momentum is going into the screen. All right, so we got the direction. Now to get the magnitude, we can say that the magnitude is going to be RP sine phi. Now P is mv, so we can rewrite this as mvr sine phi. And let's put in the numbers. 10,000 kilograms, 100 meters per second, 5,000 meters, the sine of 37 degrees, and you get 3.01 times 10 to the 9 kilogram meters squared per second. Now, to be perfectly clear, this plane is flying in a straight line, but it is doing a really bad job, if you will, of trying to rotate around me. And so that's why we still have to be able to define an angular momentum in order to get everything to work for it. All right. So with that in place, that will now allow us to revisit Newton's second law applied to rotations. Oops. So our strategy here is we're going to imagine, say, some object. And let's say this is my rotation axis right here. Actually, let's make that in red. And what I'm going to do is I'm just going to focus on a point where I am applying a force. So let's go ahead and apply a force right there. So, consistent with how we defined angular momentum, we can do a vector definition of torque here. We will say the vector definition of torque is R cross F. So at least with all these angular quantities, it's always R crossed into something, if that helps you to remember the order. Anyway, go ahead and take just a quick moment here to figure out which way the torque points. All right, so hopefully you redrew this with the vectors sitting together tail to tail. And so again, the R vector will go along the index finger of your right hand, and then the F vector will go along the middle finger of your right hand. And so then you should find that your thumb is pointing out of the screen. So yeah, here we go. So our torque vector is pointing out of the screen. All right, so now thinking back to doing this for just a single point mass, so back to our really crappy airplane, I can go ahead and remember Newton's second law, which says F net equals dp dt. And I do want to write it in the time derivative format here. Now, it will be equally true that if I cross R into both sides, that's still going to be a true thing. So I will have R cross F net. That will equal R crossed into dp dt. All right. So on the left-hand side here, I'm going to go ahead and say, oh, gee, that sure sounds like the net torque. And it totally is. But now with this right hand side here, I'm going to pull a little bit of mathematical sleight of hand. I'm going to say, think about the quantity d dt of r cross p. So the cross products obey the product rule just like normal products do. And so this is going to be dr dt crossed with p plus r crossed with dp dt. All right. Now, dr dt, that's v, the velocity, cross p. And then this bit right here, the r cross dp dt, is what we have over here. Now, you should be able to convince yourself that v cross p is equal to 0. Why is that? Go ahead and pause the video and get back with me. Okay, the reason is because p and v always point in the same direction. So the angle between them is 0. The sign of 0 is 0. So v cross p is the null vector. So what that means in this case here is where I see this r cross dp dt business, I can replace that with d dt of r cross p. But r cross p is the angular momentum. So I can rewrite this as the net torque equals dl dt. Now, if I have more than a single point mass, this is still true, but I will just assert that, again, for the special cases we mentioned, things rotating around their long and short symmetry axes, that sort of thing, we can also write this as I times alpha. All right. But that will allow us to analyze some more complicated things, like this contraption here. This contraption is known as a gyroscope. It's just a massive disc that's spinning pretty fast, and you can see it's free to rotate around on its base. So the question is why isn't it immediately flopping over? All right, so what the heck is going on? Why isn't the gyroscope flopping over? Well, that's a really good question, isn't it? Just to make it a little easier to think about here. So the phenomenon here is called gyroscopic precession. Just make it a little easier. I know in the video clip I had the gyroscope angled a bit, but you can, with patience, get it rigged up so that it's perfectly still like that. All right. So the way I had it spinning in the video, really hard to tell because I had it spinning pretty fast. I had it spinning like that. So that means the angular velocity and thus the angular momentum will be pointed along the axis like that. All right. Now let's go ahead and draw in the forces that are acting on our gyroscope. So we have the force of gravity down. And we have, I'm going to break the normal force up into the z component and the radial component here. But we have a normal force from the pedestal acting on it. Now, the reason it isn't falling is because the force of gravity down and the normal force up cancel. Now you see it precessing around like this. That's because the normal force here to the side in the little pedestal. It's a bit of a curved cup in order to give that shape. Here we go. I'll exaggerate that a bit. The normal force from the pedestal like that is providing the centripetal force to make the thing go around. All right, so this is the view from the side. Now, let's take a look at it from above. So this is the view from above. So here's our pedestal. There's our gyroscope sitting out like that. So once again, we have the angular momentum pointing out, and that's the only bit that we're really going to need here. And I'm going to draw it all the way out from there for reasons that'll make sense in a moment. All right. Now, our axis of rotation is here and there. So this means that the normal force doesn't exert any torque because both of their lines of action go through the axis of rotation. So the only bit that does exert a torque is going to be the force of gravity. So go ahead and figure out which way the torque points. Okay, again, hopefully you did something like this, where you went ahead and drew the two tail to tail like that to make it a little easier to think about. When you do the right hand rule, the index finger is going to point along R, the middle finger is going to point along FG, and you should have gotten that the torque is going into the screen. All right. Now, let's think about what happens over just a very small differential amount of time. So by Newton's second law applied to rotations, we can say that the torque is equal to dl dt, and I can rewrite that as dl equals tau times dt. Or again, I'm doing my usual physicist trick of thinking of dt as the world's tiniest delta. But now, here's the thing. If the torque is going in here, the change in the angular momentum will have to point in this view. It'll point into the screen. And in this top view here, it will be perpendicular. So a very small amount of time later, there's your new angular momentum. And since the gyroscope is a symmetric object, the angular velocity would have to point the same way. And so we end up getting that this is our direction of precession. Like that. Now, just to allay any fears, this vector isn't actually getting any longer, and that's because this dl is of differential length. So just like we saw before, if I had an acceleration a linear acceleration that was pointed perpendicular to the linear velocity, that all you did was change the direction. The same thing is absolutely true here too. So these two are actually of the same length. But it's just a trick of the differentials here. All right. So that's what's going on. In a certain sense, the gyroscope is falling, sort of. I mean, it's not. I mean, the stand is holding it up. That's what's going to keep it from falling down. But gravity is making it precess around the pedestal. So it's sort of spinning things like to fall around, if you will. And this is actually something that, say, pilots have to take into account. although most navigation now is done using global positioning system, you still maintain separate backup units, including a thing called a gyro compass, which is what it sounds like. It's a gyroscope that you spin up on the ground and a motor keeps it spinning. And the whole point here is that the faster this is spinning, the bigger the angular momentum is. The bigger the angular momentum, the slower the precession will be. So you spin it really quick so that the gyroscope doesn't precess very much. So you go ahead and you have the thing pointing north to begin with, and since it's precessing very slowly during the length of a flight, it will still keep pointing more or less north, regardless of any weirdnesses that might be happening with local magnetic fields that would make your magnetic compass not trustworthy. But for long enough flights, the pilot will have to take into account that the gyroscope is precessing, and so they'll have to make regular adjustments to their gyro compass to make sure that the instrument is still displays north correctly. Alrighty. In the next video, we'll go ahead and take a look at what is happening in torque-free situations, where we can, again, apply the conservation of angular momentum. So we'll see you in the next video.